Emmy Noether, the woman who reshaped physics. In the early 20th century, when science and mathematics were undergoing great upheaval, the story of Emmy Noether stands out as one of the most extraordinary. With her revolutionary contributions, Noether not only changed the way we understand physics, but also challenged deep-seated societal and academic prejudices. However, the journey was not easy, and her story is filled with controversy, from being excluded from academic opportunities to the way her discoveries were underestimated throughout her life. A difficult beginning. Born into a Jewish family in 1882, Emmy Noether grew up in Erlangen, Germany. Her father, Max Noether, was a renowned mathematics professor, and from a young age, Emmy was fascinated by numbers and the mathematical theories he studied. However, women were considered unsuitable for the rigorous sciences at the time. In fact, German universities did not allow women to attend formal studies. Despite the obstacles, Emmy did not give up. She was given special permission to attend lectures at the University of Erlangen, but only as an unofficial audience. This meant that she could not receive any credit for her efforts. During this time, she faced blatant sexism from both her classmates and her professors. The Göttingen transition. In 1903, Emmy Noether arrived at the University of Göttingen, a world-renowned center for mathematics and physics. There, she met important figures such as David Hilbert and Felix Klein, who would later become her greatest allies. However, her path in Göttingen was also full of challenges. When Hilbert and Klein proposed that Emmy be appointed as a lecturer at the university, the scientific committee flatly refused, saying, "We cannot allow women to teach at the university, because that would disrupt all academic order." Emmy continued to work for free under Hilbert's guidance, however. It was at Göttingen that she began to delve into the principles of symmetry and their connection to theoretical physics. The energy controversy and Noether's solution. When Einstein introduced his general theory of relativity in 1915, he ushered in a scientific revolution. But at the same time, he created a major problem: how to explain the conservation of energy in this new context. Einstein's field equations did not directly show that energy was conserved. This puzzled not only him, but also other leading mathematicians, including Hilbert. Hilbert searched for an answer, but his results were not convincing. That is when he assigned the task to Noether. Within a few months, Emmy Noether solved the problem by presenting her own theorem, Noether's theorem. Noether's theorem proves that every continuous symmetry in nature corresponds to a conservation law. For example, time symmetry leads to conservation of energy. Spatial symmetry leads to conservation of momentum. Rotational symmetry leads to conservation of angular momentum. Noether's work not only clarified problems in general relativity, but also reshaped the foundations of particle physics and later quantum mechanics. Rebuttal and underestimation. However, when Emmy published her discovery, it did not receive the attention it deserved. Partly because of gender bias, many of her male colleagues in mathematics and physics were reluctant to acknowledge the contributions of a woman, especially a Jewish woman, during a time of rising anti-Semitism. Part of this was due to the complexity of the theorem, which was beyond the understanding of many at the time. Even Einstein, who directly benefited from the theorem, initially failed to recognize its significance. It took decades for Noether's theorem to become widely recognized as one of the most important discoveries in the history of physics. Legacy and influence. Today, Noether's theorem is not only the foundation of modern theoretical physics, but also a symbol of perseverance and timeless intellect. Emmy Noether overcame social barriers to prove that intelligence knows no gender. Her story reminds us that scientific progress comes not only from great minds, but also from courage and determination to break boundaries. Emmy Noether and Einstein. Over the next 12 years after Noether earned her doctorate in mathematics, she emerged as one of the world's leading experts on symmetry. Her sharp thinking and ability to grasp complex mathematical relationships earned her the respect of her peers, including such luminaries as David Hilbert and Albert Einstein. Noether was not only the second woman in Germany to earn a doctorate in mathematics, but she was also a pioneer in applying mathematical theory to fundamental physics. One of the major problems at the time was the conservation of energy in Einstein's general theory of relativity, a problem that troubled Einstein so much that he proposed a new conservation equation. According to Einstein, if you add the energy of matter to the energy of the gravitational field, the total must be constant, and its variation over time and space must be zero. This was a major step forward in the quest for a unified theory. But when Noether examined the equation, she immediately realized that it ignored a fundamental principle of general relativity: symmetry. Noether showed that Einstein's equation violated a core idea of Saint's own theory, that the laws of physics do not depend on the frame of reference. While Einstein had attempted to extend the principle of relativity from inertial frames to accelerating frames, he had overlooked the deep connection between symmetry and conservation. Noether, with her sophisticated mathematical insight, realized that every conservation law was tied to a fundamental symmetry. This was no small intellectual confrontation, because it not only challenged parts of Einstein's work, but also called into question his approach to gravity. The contradiction in the quest. The conflict became more apparent as Noether and Einstein began to exchange ideas. Einstein, accustomed to being at the center of the scientific revolution, did not initially take Noether's objections lightly. However, he was not a conservative. When Noether explained that the principle of conservation of energy in general relativity needed to be redefined based on the symmetry of space-time, Einstein began to see the logic in her argument. Noether demonstrated that symmetry, or more specifically, invariance under transformations, was the root cause of conservation laws. This is the content of Noether's theorem, a work considered one of the greatest mathematical contributions to theoretical physics. She showed that in general relativity, energy is not conserved in the usual way, because the space-time of the universe is not always flat. Instead, the concept of conservation must be replaced by a more complicated quantity related to the curvature of space-time. The Enlightenment moment. Einstein, though confident in his own work, could not help but be impressed by the precision of Noether's reasoning. He realized that her mathematical approach could solve problems he had only vaguely imagined. Their dispute was not just a technical one, but also a meeting of two schools of thought: Einstein's physical intuition and Noether's precise mathematical thinking. A crucial turning point came when Einstein connected the ideas of accelerated motion and gravity. In what he called the happiest thought of his life, Einstein imagined a window cleaner falling freely from a building. In free fall, the person would not feel his weight, and any object he dropped would remain at rest relative to him. Einstein realized that free fall and the effects of gravity had a fundamental equivalence. This idea led to the equivalence principle, one of the foundations of general relativity. Noether's theorem and general relativity. But for general relativity to be complete, Einstein needed Noether's theorem. She provided him with the mathematical tools he needed to prove that the equations of general relativity not only satisfied the equivalence principle, but also conformed to symmetry principles. This ensured that his theory was not only physically correct, but also mathematically rigorous. The collaboration between Einstein and Noether despite its tensions and disagreements, left a profound mark on the history of science. It not only demonstrated the value of combining fields of knowledge, but also showed that scientific truth, regardless of who it came from, needed to be respected and listened to. In this journey, Noether not only helped to perfect Einstein's theory, but also affirmed the indispensable role of mathematics in exploring the mysteries of the universe. General covariance. When Einstein developed his general theory of relativity, he faced a difficult problem: how to describe gravity as a property of curved spacetime that does not depend on the coordinate system. To solve this problem, Einstein used special mathematical objects called tensors. Tensors, like vectors, are mathematical objects that can be transformed from one coordinate system to another without changing their nature. Essentially, tensors allow Einstein to describe physical quantities in a curved spacetime that are not affected by how we measure or define the coordinate system. However, the problem does not stop there. When Emmy Noether, one of the most brilliant mathematicians of the 20th century, studied Einstein's equations, she discovered a profound weakness. While Einstein's conservation of energy equation seemed to hold true in a certain frame of reference, she found that energy was not conserved when moving from one frame of reference to another. In particular, she discovered that one component of Einstein's equation, called a pseudotensor, was not really a tensor in the true sense. When she tried to apply a coordinate transformation, she found that it did not hold true under changes in reference frames, and therefore could not be considered a true tensor. This was a revolutionary discovery, as it broke Einstein's principle of conservation of energy. At least when applying transformations from one frame of reference to another. While some saw this as an inevitable consequence of a theory that described the universe in a curved space-time, Noether saw this non-conservation as a fundamental problem that scientists needed to solve. However, this contradiction was not a major obstacle in the development of general relativity. In fact, Einstein did not completely deny Noether's findings, but simply emphasized that his theory should be considered a model describing reality, not a perfect system without any assumptions. However, what Noether pointed out became an inspiration for later research in quantum field theories and modern cosmology, where equations and mathematical objects are constantly evolving. Noether, in her later years, continued to work on conservation principles and the transformation between coordinate systems in physical theories. She developed a famous theory called Noether's theorem, which shows that every symmetry in nature corresponds to a conservation theorem. Although her theory did not completely solve the problem of pseudotensors in general relativity, it did expand our understanding of the relationship between symmetry, conservation, and physical theorems. Combining Einstein's principles with Noether's contributions, later scientists developed quantum field theory, supersymmetry, and other modern physical theories, where the understanding of tensors and energy conservation continues to be clarified and developed. However, the problem of non-conservation in different reference frames remains a major open question in modern cosmology and in the quest for a theory of everything. The story of Einstein, Noether, and their mathematical discoveries remains a clear example of the evolution of science, where theories may clash and change, but it is in these disputes that science finds constant progress. The time symmetry that Noether was talking about opened a very important door to a deeper understanding of the universe and physical theorems. She realized that if the physical theorems do not change over time, meaning that the results of an experiment today will be exactly the same as the results of the same experiment tomorrow, then the universe can be said to be, in some respects, unaffected by the passage of time. This means that time in the universe has a balanced, or balanced, quality, not shifting or changing over different periods. The question Noether asked was, if this symmetry existed, what conservation principle in the universe would it lead to? And the answer she discovered was the conservation of energy. She argued that the constancy of physical theorems over time, or time symmetry, is the reason why energy is conserved in all systems. Any change in the system, if any, must leave the total energy the same, because nothing outside the fundamental laws of physics can change the total energy of a system. Now, with this insight, Noether realized that the universe was not a chaotic entity that arose randomly from discrete principles. In fact, it was organized around solid principles of symmetry and conservation, which we could understand and predict through mathematical formulas. However, figuring out how we could relate them together remained a challenge. It was for this reason that Einstein had difficulty trying to incorporate the concepts of energy conservation into general relativity, because in this context, energy could not be defined as simply as in older physical theories. In general relativity, gravity is seen as a warping of space and time, and this creates a complication in determining the total energy of a physical system when space and time are no longer flat entities. However, for Noether, what was important was that her understanding of symmetry was not just a tool for explaining physical phenomena, but also for identifying the connections between different types of symmetries in the universe. Not only are there symmetries of space and time, but there can also be other types of symmetries, such as symmetries in the fundamental forces, symmetries in the structure of elementary particles, or symmetries in the coupling of quantum fields. Thus, each symmetry in the universe, according to Noether, is a different conservation principle, forming a strong network that we can use to explain everything from the motions of large celestial bodies to the microscopic phenomena of quantum particles. It is a world where everything is connected in such a way that only by discovering their symmetries can we understand why the universe works the way it does. Noether's contribution not only helped us understand the fundamental laws of physics, but also opened up a new way for us to think about the universe, not as something random, but as a system with clear order and symmetry. The universe is not just a collection of objects and forces, but a network of symmetries that bind these elements together. And that is why the principles of conservation of energy and momentum exist. We can imagine that every change in a system, whether the movement of a ball or the change in the structure of an elementary particle, obeys these symmetries. And while we may not understand all of those symmetries right away, one thing is certain. These symmetries are the key to unlocking the secrets of the universe. So when Noether looked at the challenges Einstein faced, she realized that the answer was not to apply a simple conservation rule to general relativity, but to understand that every system in the universe can be described by a series of symmetries, and that those symmetries are the foundation for understanding the conservation of energy, momentum, and every other physical principle. Noether had come up with a whole new way of looking at the universe, not just as a set of physical laws, but as a harmonious system of symmetry that we are still trying to discover every day. This, of course, would change the way we look at the universe, and not just physics, but science in general. And perhaps in the future, as we solve the greater mysteries of symmetry, we will discover that the universe is indeed a beautiful entity, not just because it exists, but because it operates according to subtle symmetrical principles that we are only just beginning to understand. Principle of least action. To understand the principle of least action, we need to dig into some new math and approaches to doing mechanics. This principle is not just a mathematical concept, but also the foundation of many inventions in modern physics. Previously on Veritasium, we learned that everything in nature always follows a path that minimizes a quantity called action. Action in physics is defined as the integral of the Lagrangian L with respect to time. In its simplest case, the Lagrangian is just kinetic energy minus potential energy, a beautiful yet powerful expression that opens up a new way of looking at natural phenomena. Leonhard Euler and Joseph Louis Lagrange proved that the principle of least action is always respected if the Euler-Lagrange differential equations are satisfied. These equations are not only mathematical tools, but also bridges between theory and experiment, helping us to better understand how the world works. Sophie Noether, a great mathematician, took this principle to the next level. She used action to explore how different symmetries in nature affect the laws of physics. One of her most important discoveries was the connection between symmetry and conservation laws. This completely changed the way we look at natural phenomena. Imagine an experiment where the outcome does not change over time. That is, if you observe an event now, the outcome remains the same after a small epsilon of time. The question is, how does this affect action? When time changes from t to t plus epsilon, the Lagrangian will also change. The new Lagrangian will be a prime L, which is equivalent to the old Lagrangian, plus the rate at which it changes with time, expressed as dl dt times epsilon. But remember, the result remains the same, no matter how small epsilon is. This leads to an important fact. dl dt does not affect the equations of motion. This is the key to understanding that from the symmetry in action, we can deduce the conserved quantities. Let's take a closer look. If we take dl dt and apply the chain rule, we get the partial derivative of L with respect to position x, multiplied by dx dt t, plus the partial derivative of L with respect to velocity v, multiplied by dv dt t. However, from the Euler-Lagrange equation, we can replace the partial derivative of L with respect to x with a different expression. This leads to a simpler form, the time derivative of dl dv multiplied by v. The next step, when we take dl over dt to the right, we realize that the time derivative of this quantity is 0. That means this quantity must be a constant. This is the key point. This constant reflects a conservation law in nature. Now let's apply it to the simplest case, where the Lagrangian is just kinetic energy minus potential energy, that is, 1/2 mv2 v. The partial derivative of L with respect to v will be m multiplied by v. Applying the mathematical steps, we see that the total energy, including kinetic and potential energy, is always conserved. This is the law of conservation of energy, one of the most fundamental and powerful laws of physics. This discovery raises a controversial question. If time symmetry means that energy is conserved, can we find other symmetries that correspond to other conservation laws? And do these laws hold in all systems, even nonlinear or unstable ones? The controversy arises when we try to apply this principle to other fields, such as quantum mechanics or relativity. In quantum mechanics, the minimal action is replaced by Feynman's path integral, opening up a new and challenging but also extremely promising direction. In relativity, the concepts of time and space are no longer fixed, raising the question of how time symmetry works in a curved dynamical system. These questions not only challenge us intellectually, but also drive the development of theoretical physics. We are on the threshold of new discoveries, where the principle of least action is not just a mathematical tool, but the key to unlocking the secrets of the universe. Noether's first theorem, the principle of conservation of energy and controversies, symmetry and conservation laws. The principle of conservation of energy has long been considered one of the fundamental pillars of physics. It is a direct consequence of time symmetry, a revolutionary concept proved by Noether's theorem in the early 20th century. Emmy Noether, one of the most brilliant mathematicians in history, showed that every continuous symmetry of nature leads to a conservation law. Spatial translation symmetry leads to conservation of momentum. Rotational symmetry leads to conservation of angular momentum. Time displacement symmetry leads to conservation of energy. This result has led to a deeper understanding of the laws of nature and explained why conservation laws are not just random observations, but inevitable consequences of the mathematical structure of the universe. The expansion of the universe and the breaking of symmetry. However, in the 1920s, Edwin Hubble's astronomical observations shook up our understanding of the universe. He discovered that distant galaxies were receding from us, and that the rate at which they were receding was proportional to their distance. This showed that the universe was not static but expanding. In the 1990s, measurements of type Ia supernovae made an even more surprising discovery. Not only was the universe expanding, but the rate of expansion was accelerating over time. In other words, the universe was asymmetric in time. This raised a fundamental question. If the universe was not time-symmetric, would energy still be conserved? Energy in the expanding universe. Imagine a photon of light emitted about 380,000 years after the Big Bang. As this photon travels through the expanding universe, its wavelength is lengthened due to the redshift effect. The lengthening wavelength means that the photon's energy has decreased. But where did that energy go? The controversial answer is, it went nowhere. Energy in this context is not conserved. This seems to contradict everything we have learned. But on closer inspection, it is consistent with the fact that energy conservation only applies when the universe has time symmetry. In an expanding universe, this symmetry does not exist, and there is no reason to expect energy to be conserved. Philosophical and scientific implications. This finding has implications not only for physics, but also for profound philosophical debates. If energy is not conserved, what implications does this have for other fundamental theories of physics? Do familiar concepts such as momentum, mass, and spacetime need to be rethought in the context of cosmology? Some physicists argue that abandoning the principle of conservation of energy in an expanding universe does not undermine physics, but makes it more precise. Rather than trying to maintain conservation laws in all contexts, we should focus on understanding the limits of their applicability. Why does energy appear to be conserved? Although the above arguments sound convincing, in everyday practice, energy appears to be conserved. This is because most of the phenomena we observe occur in systems where time symmetry is largely unbroken. For example, in a physics laboratory, cosmological effects such as the expansion of space are negligible. But when we extend our observational horizon to the entire universe, these effects cannot be ignored. This distinction between the microscopic and macroscopic views is the key to understanding why energy appears to be conserved in small systems, but not in the universe as a whole. Opposition and controversy. Some scientists disagree with this approach, arguing that it undermines the fundamental principles of physics. They argue that a unified theory is needed to explain both cosmology and microphysics, without abandoning conservation laws. Proponents of the new view, on the other hand, see it as an opportunity to broaden our horizons and ask new questions about the nature of reality. The story of energy conservation in an expanding universe is not only a physics lesson, but also a reminder that our knowledge of the universe is limited. It raises larger questions about how we understand and define the laws of nature. Are they immutable truths, or just temporary tools we use to understand the world around us? The expanding universe has changed the way we see everything, from photons of light to the fundamental principles of physics. And in the process, it reminds us that science never stops evolving, and that what seems obvious is sometimes just the beginning of a new journey of discovery. The continuity equation. As Noether continued to expand the concepts of symmetry and conservation in a curved universe, a major question arose. How could energy be conserved in a space-time that was constantly changing, stretching and bending? This was a question that the likes of Hilbert and Einstein had previously been unable to answer satisfactorily. However, in a moment of inspiration, Noether saw a possible solution in her equations, making them an important piece of the cosmic puzzle. When she imagined the pipes not as simple water pipes, but as small patches of space-time, we begin to envision a more complex system. In these patches, water, or rather energy, still flows in the way we know it in classical physics, in small patches of space-time where energy can be clearly conserved. But the real problem comes when you put these pieces together, and you see that the curvature of space-time can change the way energy moves. These are like cracks appearing between pieces of space-time, where energy can leak through. This is where Noether discovered the additional elements in her continuity equation. These elements include not only classical physical quantities, but also changes in gravitational fields, an essential element of general relativity. Since space and time are no longer static but constantly changing, we have to consider how gravitational fields affect the movement of energy in the universe, making the conservation of energy much more difficult. And sure enough, Noether showed that these changes could be described by the continuity equation. What made things more complicated, however, was the interpretation of these equations in the context of curved space-time. This led to a major turning point in theoretical physics. By calculating the interaction between energy and space-time curvature, Noether discovered a way to defend the conservation theorems of general relativity. Although Hilbert had previously rejected this, arguing that it only applied to empty universes and was not valid in universes with matter, Noether showed that this was indeed the only way to solve the problem of energy conservation in general relativity. Noether's contributions were not limited to solving a problem of energy conservation in an expanding universe. She also extended the conservation theorems to local symmetries in curved space-time, demonstrating that these symmetries existed and could explain many physical phenomena that physicists had not previously been able to explain. She discovered a connection between local symmetries and conservation theorems, thereby providing a new way to understand phenomena in the universe more fully. This, of course, was not easy for the physics community to accept. Noether's theories challenged the deeply held views of physics, where scientists still believed in classical physics and were reluctant to accept major changes. Meanwhile, prominent physicists such as Hilbert and Einstein, while appreciating Noether's discoveries, had mixed reactions to the theories that broke old ideas. This was especially true in the context of general relativity, a complex theoretical system that they had spent decades developing. However, Noether's contributions soon began to be widely recognized. The University of Göttingen, where Noether taught and worked, soon recognized her value. They promoted her to professor and allowed her to continue teaching and researching. In 1923, Noether was given an official salary, which, although very small, was an important step, marking official recognition of her contributions to science. But what is interesting here is that, despite Noether's great achievements in physics, she still faced a lack of recognition from the academic community, especially in a scientific context that was still strongly dominated by conservative ideas. Noether's discoveries, although revolutionary, were not fully accepted, and the controversy over her theories continued to rage. Noether's story is not only the story of a great scientist's career, but also a fight to prove that in physics, truth can change and progress, even in the face of skepticism and controversy. Her perseverance and intelligence opened a new era in our understanding of the universe and the laws of physics, demonstrating that sometimes just a different perspective can change the world. Escape from Germany. On January 30, 1933, when Adolf Hitler came to power and the Nazis banned Jews from working in universities, Emmy Noether, one of the greatest mathematicians of the 20th century, found herself in a difficult situation. Because of her Jewish heritage, she was suspended from the University of Göttingen, where she had taught and researched for many years. But despite the oppression and discrimination, Noether never gave up her passion for mathematics. Although she was no longer a lecturer at the university, Noether continued to research and teach from her small kitchen, where informal lessons continued. One day, a former student of hers, wearing a brown Nazi stormtrooper shirt, knocked on her door. It was a controversial event, but Noether, a woman devoted to mathematics, did not discriminate and welcomed her students into her home to continue teaching. Her enthusiasm and dedication to mathematics was not deterred by the threats from the regime. This was most evident in her continued teaching, despite the unfavorable and dangerous conditions. While many would have given up easily, Noether stood firm, committed to imparting knowledge no matter the hardships she faced. An important aspect of her character was her ability to overcome all personal hardships, not only to protect herself, but also to protect the values she believed in: freedom of research, a belief in academic equality, and an undying passion for mathematics. However, life in Germany under the Nazi regime gradually became untenable. Fortunately, her connections with international scholars, especially her colleagues in the United States, opened up new opportunities for her. With the help of Albert Einstein and other friends, she was offered a teaching position at Bryn Mawr, a prestigious women's college in the United States. It was a valuable opportunity, allowing her to continue her research in a free environment and free from political threats. At Bryn Mawr, Noether continued to make important contributions to mathematics, especially in the theory of symmetry and invariance. Noether's theorem, published in 1915, became one of her greatest contributions to mathematics and theoretical physics. It linked symmetry with conservation theorems in physics, and is an essential tool in modern theories of particle physics and astronomy. The theorem was not only a turning point in the understanding of conservation theorems, but also a powerful tool in quantum field theory, general theory, and other branches of modern physics. Einstein, who greatly admired Noether, wrote in her obituary, "Fraulein Noether is the most important creative mathematical genius that has been produced since women received university education." Einstein's praise demonstrated Noether's importance, not only to mathematics, but to the entire world's scientific community. Noether's theorem, as Einstein pointed out, was a turning point not only in mathematics, but also in the way physicists think about the universe. The discovery of the connection between symmetry and conservation theorems opened a new era in the study of natural phenomena. Noether's life is an inspiring story of resilience and passion for science. She overcame gender barriers, political oppression, and personal hardships to become one of the greatest mathematicians of all time. Her work, especially Noether's theorem, continues to have a profound influence on fields such as theoretical physics, astronomy, and even computer science. What she contributed to science and how she devoted herself to her work is a living testament to the power of unquenchable passion and intellect. The Standard Model, Higgs and Quarks. When Noether first entered the world of mathematics, she not only followed in her father's footsteps, but also had to overcome many difficulties due to the gender discrimination of the time. But even when faced with personal and social challenges, she did not give up. In fact, those challenges only pushed her to delve deeper into the theories of symmetry and conservation in physical systems. She had the ability not only to see what others did not see, but also to completely reshape the way we understand the world around us. What Noether discovered was that the symmetries in her theorems could help explain some seemingly unsolvable problems in physics. For example, the symmetry of electromagnetism can be linked to the conservation of electric charge. And similarly, the symmetry of quantum field theory can lead to revolutionary results about the formation and interactions of elementary particles. Not only did Noether's discoveries help explain phenomena that were already known, they also opened up new possibilities for how we might approach and understand the universe. This led to one of the most important advances in theoretical physics, the discovery of elementary particles such as quarks and the Higgs boson, which in the late 20th and early 20th centuries became indispensable research subjects in experiments at facilities such as CERN. These particles are not only the building blocks of matter, but also the keys to expanding theories about the origin and structure of the universe. With Noether's theories, physicists not only understood how forces work in the universe, but also how mass is created. This is one of the great questions of modern physics, and it became the foundation for the development of theories such as the Standard Model of nuclear physics. But Noether's influence was not limited to physics. The principles she developed about symmetry and conservation have spread to various fields, from mathematics to information theory, and even the theories of complexity in systems. These theories continue to help us better understand how the universe works, from the most fundamental particles to large-scale structures like galaxies. Looking back on Noether's journey, we see an important lesson about curiosity, perseverance, and innovation in science. She started out as an ordinary mathematics student, but with patience and love for mathematics, she built a theory that has had a profound influence to this day. And as Noether's story goes, learning is not just about absorbing knowledge from those who came before, but also about asking questions and finding answers yourself. Finally, if viewed from a broader perspective, the theories that Noether contributed were not only the key to unlocking the mysteries of physics, but also reflected a profound philosophy about understanding the world. That is, the constant interplay between symmetries, conservation, and the unpredictable movements of the universe.